So I'm going to talk about directed polymers in a random environment. Okay, starting to prepare things, I realized that perhaps it will be difficult to remain just a full month on the subject, so perhaps we will do something else in the end. But okay, this is what will occupy the 2.5 at least to 3 next weeks. Okay, so directed polymers. Okay, and well, just let me make a small introduction about what is a statistical mechanics model in general, this implies telling you the truth about something. Perhaps, in a sense, random walk in a random environment is not a statistical mechanics model, but it's very close to be one. So, okay, so. So yeah, when you do statistical mechanics, what you have is a state space. So okay, it will be finite. It takes exponential growth. It's not mandatory, but it's basically what's typically happens. The other ingredient is Gibbs weights. So for x in the state space, okay, we are going to associate a quantity, a positive quantity, okay, which is going to take the form exponential minus beta h of x. So here this beta it's a non-negative parameter that we call the inverse temperature of the system. And h, well, it's a function from omega n to r. Yeah, basically it corresponds to the energy of a state x. Okay, and once you have your state space and your Gibbs weights, what you do is you define a probability measure on omega n. Okay, let's call it P and H. Okay, it depends both on this function and on n and on beta. Okay, and what you want is that the probability of a given state is proportional to exponential minus beta hx. Okay, so basically your set of Gibbs weights, okay, it defines a finite measure on omega n, okay, and you renormalize it just in order to make it a probability. Okay, so a way to rewrite this is to say that the probability of a space of a state is 1 over z n h beta exponential minus beta hx, where z and H is equal to the sum. Okay, and basically, then there are two things you can do. So you can either, well, study the properties, typical properties of this probability measure when n grows to infinity. Okay, so this is called equilibrium statistical mechanics. Or what you can do is also study a Markov chain for which the reversible measure is this one. Okay, and wonder about how this Markov chain behaves. Okay, how you converge to equilibrium, or any other thing you want. Okay. The first thing is called equilibrium statistical mechanics, and the second out of equilibrium statistical mechanics. And in a sense, random walk in a random environment, it's more akin to out of equilibrium statistical mechanics, in the sense that you're looking at a Markov chain, which is reversible with respect to a set of Gibbs weights. Okay, it's just that the set of Gibbs weights, it's not summable, so you don't have a probability measure behind. Okay, so this is your general framework, and now I'm going to tell you what's going to be omega n and h for us in the next few lectures. Any questions so far? Okay, so omega n, well, it's going to be the set of finite paths in ZD. I will put a 0 here. And I impose that they are starting from 0, and that for all n in 0, in 1n, xn is a neighbor of xn minus 1. Okay, so I don't remember how often I have used this notation before, but this is just this. Okay. This is just being neighbors in ZD. Okay, so. Sorry? Thank you. Okay, so it's a finite state space. And in fact, the cardinality of omega n, it's easy to compute. I mean, you have no choice for the x0, and then you have 2D choice for each of the increments. So the cardinality is just 2D to the power n. Okay, now comes our h. So the energy functional now it's going to be defined in terms of a random environment. Okay, so we are going to have an omega, well, therefore you will have two levels of probabilities. Okay, omega will be drawn according to some probability, and then therefore this p n that we are going to study is going to be a random probability in a sense. Okay, and as for random walk in a random environment, we are going to be interested in almost sure statements. Okay, so omega, it's Well, it's a set of numbers, okay, which is indexed by, if you want, n times zd. Okay, so here you can think about this parameter as time and this parameter as a space. Okay, and we are going to take them as the way I obtain these numbers is I have sorted them at random in an IID fashion. Okay, and we are going to have some assumptions about the distribution of omega, but I'm going to tell you about that later. I'm going to consider h and omega x, which is equal to minus the sum from n equal 1 to n of omega n xn. Okay, and therefore I define also p and beta omega of x, which is equal to 1 over z and beta omega exponential beta sum from n equal 1 to n omega n xn, where z and beta omega is the sum over x in omega n exponential sum from n equal 1 to n. Beta omega n. Okay, so just a few explanations. Why do I have a minus here? Well, it's simply so that I don't have a minus here. And now, how can you interpret this energy? So what you can say is, okay, I should make a picture. So the geometric object which is relevant here is the graph of x. Okay, so let me draw the picture in d plus 1 dimension, and let's take d equal 1. Okay, so this is my, well, one particular x. Okay, I guess n is equal to 11. Okay, and basically minus omega n x. Okay, it's the energy associated with site nx. Okay, and the energy of a trajectory, it's just the sum of the energies collected on the graph of the path. Okay, this is so. This energy of this x is just the sum of all these omegas that I have collected. And somehow I don't care about what happened at the origin. Well, first, it will be convenient for the computations. And second, it wouldn't affect the probability, okay? Because it would appear in Z and in the Gibbs weight, so it would simplify. Okay, but this is just a convention. Okay, so what can we say? Okay, first thing we can say about the behavior of x under this measure is that it's akin to visit space-time sites with low energy. Okay, it wants to remain in low energy states. Okay, so it's kind of attracted to these nx's for which the omega is high. Okay, because minus omega is the energy. So that's the first thing. So under P and beta omega, x is attracted by low energy sites, okay, meaning high values of omega and x. Okay, so this is the first observation. And B, well, this effect is stronger if beta is larger. Okay, I mean, I'm giving a bonus, well, proportional to exponential beta omega to visit a given site. So yeah, it makes me more likely to visit high values of omegas, and the effect is stronger when beta is large. Okay, so let's give you two extremal cases here to kind of to understand what's going on. Okay, and here I'm going to throw my first assumptions on first and last assumptions, I guess, on omega. So we are going to assume two things. Okay, they are not super important. It's mostly for the sake of the discussion, but if you understand, so I will call this blackboard P. Okay, it will be the law of omega, okay, of my IID environment. And I will assume first thing that okay, that my environment is bounded, okay, in the sense that, well, with probability 1, it's in the interval minus mm. And second, I'm going to assume that my environment has no atoms. Okay, so now let's study our two extremal cases. Okay, not so. So extremal cases, this corresponds to extremal values of beta. I'm telling you that beta is a non-negative parameter, so the two extremal values are 0 and infinity. Okay, so So if beta equals 0, your measure is simply the uniform measure on your state space. So basically, the distribution of x is that of the first n steps of a simple random walk. Okay, so you know pretty much everything. So when we scale, this converges to a Brownian motion. Okay, the endpoint it's distributed. It has a Gaussian distribution. You know also that the endpoint distribution is spread out. Okay, because of this local central limit theorem. I mean, we have only seen something about the endpoint distribution. I mean, okay, what you can show is that the probability that xn is equal to x. Well, this thing, okay, it's roughly exponential minus x squared over 2n. Okay. Times. Okay, let me. Okay, pxn x, it's equal to 2 square root of d over 2 pi n to the d exponential minus g x squared over 2n plus little o of 1. Okay, we have only proved that for I think x equals 0, okay, and index x and n have same parity. Okay, because if not, the probability is 0. Okay, and we have proved that, if you remember, for x equals 0, okay, using Fourier transform, but this is kind of the same proof. Okay, so in particular, okay, this thing it's smaller than c n to the minus d over 2. Okay, so the endpoint distribution is spread out. Okay, so for this reason, we say that the measure is delocalized, okay, in the sense that it can, yeah, like whether you look at the path structure or just the endpoint, basically, it kind of fills the whole space and it has no favorite spot. Okay. So now, what about B? Well, you can look at the limit when beta goes to infinity of P and beta omega x. Okay? Yeah, would anybody tell me what this limit is? Okay, so this probability, I mean, it's just the quotient between this and the sum of all Gibbs weights. Yeah, the Dirac of on the mini maximum. So the Dirac on the minimal value of h. Yes. So it's delta x min of x, where x min is the minimizer of h and beta omega. Okay, and well, this is the important thing, the minimizer. So there is a minimizer here. Okay, simply because I have assumed this. Okay, so let me just prove that there is a. Okay, with probability 1, you have a unique minimizer, and then prove that this is true. Okay, just for the sake of completeness. Any question? Lemma. P almost surely there exists a unique element of omega n, okay, which I call x min, okay, n if you want, such that h x min and beta omega is equal to the minimum over h in omega n of h and beta omega x. Okay, so the way to prove this is not complicated. What we need to prove is that it's impossible for two paths to have the same energy. Okay, so okay, and well, you see this event you have here, it's a finite union, okay, because you have this quantifier here, so you can just bound it by a sum. I mean, basically, you just need to show that the probability of this is 0 for any fixed x and x prime. Okay, so let's take x not equal to x prime, and let's show that the probability of this probability is equal to 0. Okay, so well, let's use this assumption. So consider n such that xn is not equal to x prime n. Okay, this exists because the two paths are different. So P of hx equal to x. Well, this is the probability that omega n xn well, it's equal to hx minus hx prime and I guess I have to add plus omega n xn. Okay, I've done nothing here, but here the thing is that okay, this thing, it's a function of omegas at every site but this one. Okay, because here you have minus omega n xn, and I'm adding it here. So you have no dependence. So this belongs to, well, sigma omega kx different from nxn. Okay, so in particular, this thing is independent of that. Okay? So basically now I can use, if you want, Fubini or anything you want. But what I can say is that this is equal to, well, the expectation of the probability that omega n xn is equal to, well, okay, let me write this down. Sum from k equal 1 to n omega k x prime k minus sum k in 1 n minus n omega k x k. Okay, so here you really see that this thing and these things are independent. Now I can condition to this. Okay, so let me call this f circle and xn. Okay, and now this conditional probability, it's equal to 0. Okay, conditioning here, it means that you can consider this as a fixed number, and my probability has no atom, so this is equal to 0. Okay, another way to see this is that this is just, this is expectation with respect to a product measure, so you can do Fubini, and you're integrating along some kind of diagonal here, okay, which has 0 probability. Okay, so we're good. So we have proved the lemma. Okay, so now let's prove this, which is easier. So what you have is that is not equal to x min. Okay, what you have is that p and beta omega x. Well, okay, it's this divided by that. Okay, in the sum, I can just keep the largest term. Okay, so it's smaller than exponential minus beta hx divided by exponential minus beta hx min. Okay, so beta hx min minus hx. Okay, this thing is negative, beta goes to infinity, so this thing, when beta goes to infinity, it's equal to 0. Okay, and well, then you have this thing is a probability. So if you look at x min, well, this is 1 minus the sum over x. Okay, there are finitely many terms. Each of these converge to 0, so this converges when beta goes to infinity to 1. Okay, so when beta goes to infinity, your measure, I mean, it behaves like kind of the opposite as a simple random walk. I mean, instead of being uniformly spread of your state space, it's concentrated on one path. And well, the same is true for any observable. So in particular, if you look at the endpoint distribution, it's also, well, Dirac mass of the endpoint of x min. Okay. So now comes the notion that is very fundamental in statistical mechanics, is that of phase transition. So what we want to understand is how do we transfer, okay, from one regime where you have this spread out behavior to one regime where basically you occupy a tiny fraction of the state space. Okay? And the whole idea is that this transition should be abrupt. So okay, we will try to find some value of beta okay. Okay, let's say that we allow for the value 0 and infinity. We will see in the end that it's not really necessary. Okay, but okay, we'll be happier somehow if it's not 0 and not equal to infinity. Okay, and such that, well, if beta is smaller than beta c, then the behavior of the system is similar to the one when beta is equal to 0. Okay, and with the vaguest possible notion of what similar means. Okay. Okay, and 2, if beta is larger than beta c, then okay, in a sense, okay, the behavior should be similar to the beta equal infinity one. Okay, so again, I'm very vague there, but what we mean is that really the support of this measure is really a tiny fraction of the state space in a sense that has to be defined. Okay, and here when I mean tiny, somehow the cardinality of the support is not the right way to quantify things. Okay. Okay, so this is Okay, this is a very brave prediction in a sense, and it might also look a bit stupid because here you're looking for something very abrupt. Okay, and if you look at the expression that I have for the probability of a path, okay, it's not there anymore, but okay, okay, if you look at the expression of your Gibbs weights, okay, they're not only continuous in beta. They are in fact C infinity in beta, and they are even analytic in beta. So the behavior in beta varies very, very smoothly. Okay, so to have some kind of discontinuity in the typical behavior of X is a lot to ask. But here the thing is that we are going to look at properties that are true for very large systems. Okay, so we are going to look at the limit when n goes to infinity. Okay, and physically it makes sense because basically statistical mechanics model, they are supposed to describe how things behave at the atomic scale. So if you want the relevant values of n, they are of order to 10 to the power 10. So okay, so it remains kind of a brave prediction, but at least it's not stupid because you know that the limits of analytic functions, they are not necessarily analytics. Okay. So, okay. Okay, and just to give you some motivation to remain in the class. Okay, no, just to tell you what the kind of things we are going to prove. Okay, I'm going to identify you. Okay, so we are going to prove that such a beta C exists. Okay, and then I have to tell you, yeah, what version of this thing are we going to prove? Okay, so I'm going to look at mu n x, which is p and beta omega x n equal x. So, okay, I'm going to give you more results than just this, but let me tell you here just about the result about the endpoint distribution. So mu n it's a probability on ZG. Yeah, it's just the distribution of the endpoint of my polymer under the polymer measure. Okay, so if beta is smaller than BC, then the limit when n goes to infinity of mu n infinity is equal to 0. Okay, this is just okay, the supremum norm of my measure. If beta is more than beta C, okay, then the lim inf when n goes to infinity of the sum from n equal 1 to n of mu n infinity to divided by n is positive. Okay, so in one sense you go to 0. In the other sense, you don't go to 0 in César mean. Okay, and in a sense, César mean is the best you can expect. Okay, you have IID environment. So by Borel-Cantelli, something very special might happen at the end. So actually, it's even possible to show the limit of mu n infinity here it's equal to 0. And it's not a very interesting statement. So this is the reason why you can prove here only in a certain sense, either in distribution, but proving this in distribution is an open question. But you can prove this in series only. Okay, so okay, this phenomenon is called delocalization. Okay, just because the n-point measure is spread on a large number of points, and this phenomenon is called localization. Okay, and this thing here is called the localization transition. Any questions so far?
Will we get results for the whole path or just like
Yeah, you will get results for the whole path. But not in the localized phase, unfortunately. Okay, you can get results there, but they are not very satisfying. Yeah, the best thing would be to try to. Yeah. So okay, let me. Okay, so what could you expect for the whole path? So, path results. So, what could you expect? Okay, so let's look at something very bold. Could you expect that the maximum over x of p and beta omega x, okay, well, does not converge to 0? Okay, this would be somehow being localized in the path space. So this has no chance of being true. You have actually rather soft arguments, okay, that tell you that this thing it has to go exponentially fast. Okay, so I can tell you why this can, okay, I can show you why this has to be smaller than c over n already. Okay, so just take one path. Okay, let's imagine that it's a maximal path. Okay, by some argument you can say, okay, this path it will have to have lots of corners. Okay, it will have to turn lots of times. Okay, you cannot have super long stretch on this path because if not, basically you're not exploring the whole space. So you have lots of corners, and each of these corners you can flip them if you want. Okay, so you will just say that. Okay. Okay, so I'm considering the Hamming distance between two paths. It's a number of sites where they differ. Okay, so what I'm claiming, okay, and is that if you take the path that maximizes the energy, it has a large neighborhood in the Hamming distance. Okay, so it has a large neighborhood because you can just differ. Okay, so basically it has of order n. So x mean has of order n neighbors in the Hamming distance. Okay, because if not, it would be a very atypical path. Okay, now all things in this neighborhood, they have h which is very similar to h of x min. Okay, so they give a contribution to the partition function which is of order n times. Okay, so this gives you this. Okay, so this is really hopeless, and actually you can get this argument, push this argument a little further. Like if you look at things that are at a Hamming distance of order epsilon n, then you have exponentially many, and the weights might be decay a little bit, but somehow, yeah, not as fast as okay. Basically, entropy is going to win against energy in this competition. Okay. Basically, by allowing to differ a little bit, you gain lots of entropy. And you lose a bit of energy, but entropy gains. So this has no chance of happening, and this will actually go to zero exponentially fast. But you can hope some other thing. So you can hope that basically you have a favorite path. Okay, it's not necessarily the one with the highest energy. Okay, but you have a, and if you draw a path according to the polymer measure, well, it will spend a positive fraction of its time with this. Okay, so if you look at the overlap between the two paths, it will be something that is of order n. So this is the kind of result that can be proved. So under some condition, so for large beta, okay, you can prove that the expectation under the product measure of the number of time coordinates such that xn coincides. Well, you can prove that basically this thing, okay, does not go to zero. Okay, that basically this thing converges to some positive value. Okay, so basically, yeah, you don't have a Dirac mass, but if you rescale things, you can hope to have a Dirac mass, because if things spend a lot of time together, basically it probably means that looking from far away, all the measure lives in a very thin corridor. Okay, and this is something that people can't really prove. Like, if you just have a result like that, you cannot exclude that you may have finitely many corridors or something like that. Okay, but this is the kind of result you get. Okay, so this is for the localized part where here you get convergence to Brownian motion. So pretty neat result about the path distribution. Okay, on a large scale, the path distribution looks like the one you have for simple random walk. yeah, this is what we want to do. It requires lots of work, so let's get started. Yeah, first thing I have to tell you is that, well, what you want to do if you want to study the measure is actually you want to study the z and beta omega. Okay, so remember, p and beta omega of x, which is exponential minus beta h and beta omega x divided by z and beta omega. And well, it may not seem obvious at the beginning, but somehow knowing things about the asymptotic behavior of this sequence, okay, which is just, I mean, it's a sequence of random variables, it will give you lots of information about the asymptotic behavior of this object, okay, which is a much more complicated object, a sequence of random probability measures. Okay, so the first thing we are going to do is, well, compute. Okay, you have a random variable. First thing you might want to do is compute the expectation. Okay, so our way to prove results concerning p and beta omega is to study z and beta omega. Okay, so so first thing, the expectation of z and beta omega, it's something you can compute explicitly. It's equal to 2d to the power n times the Laplace transform of omega to the power n. Okay, so let me prove this. Okay, so this thing, okay, it's you can use Fubini. It's the expectation of a sum. So it's the sum of the expectations. Here, for a fixed path, x, this thing is a sum of IID random variables. Okay, so because you're taking the exponential, what you have is a product of IID random variables. So what you have is just the expectation of one variable to the power n. And well, because this does not depend on x, I can multiply by the cardinality. Okay. Okay, so now basically what we will try to figure out is whether the expectation of Zn is a good way to evaluate Zn. Okay, so we want to know if Zn behave like its expectation. It cannot be much larger, but it could be a priori much slower, much much smaller. Okay, so what we are going to study is the sequence Wn, and Wn is just Zn divided by its expectation. Okay, so I can rewrite it in a way which would be more convenient. So this is equal to, well, 1 over 2d to the n. Okay, this factor here goes down there. And then I get, well, the sum from over x in omega n, exponential sum from n equal 1 to n beta omega n xn. And, well, I have to divide by this. So what I'm doing is to each term, I delete lambda beta, where lambda beta, it's the log of the Laplace transform of the variable omega 1, 0. Okay, so here, I mean, I have n terms. So I'm just subtracting n times lambda beta. So what I get is really, I'm dividing by this expectation to the power n. Okay, and a way to rewrite this is to say, okay, well, here, this is an expectation. Okay, this is the expectation with respect to the uniform measure on omega n. Trouble with. Okay, and okay, if you want, you can also rewrite this as okay, I'm just deleting the n here. Okay, where here under p xn is a simple random walk on ZD. Okay, this is the distribution of the first n steps of a simple random walk. So this expectation is the same as this one. Okay, just because here what's appearing is just depends on the first n steps. Okay, so somehow, well, this gives you an alternative definition of the polymer measure if you want. Okay, so if you prefer, you can say, okay, it's omega is z to the n. Okay, so an uncountable space, and p and beta omega. Well, it's a measure which is absolutely continuous with respect to the simple random walk, and the Radon-Nikodym derivative is 1 over Wn exponential sum from n equal 1 to n. Okay, where Wn is equal to the expectation of exponential. Okay, so the expectation of this exponential, so that this thing has expectation 1, so it's indeed a probability density. Okay, so the two definitions are equivalent in the sense that, if you take this definition and then you project, you just take the push forward of the measure, just looking at the distribution of the first n steps, okay, you get the other one. Okay, and therefore the definitions are the same because here only the distribution of the first n steps are relevant. The rest is just, the rest of the increment is just distributed like a simple random walk, so you're not going to want to study that. It's not physically relevant. Okay, so I'm just giving this alternative definition because it's one you sometimes find in the literature as well. Okay, so okay, now I'm going to state a theorem that we are going to, we are going to need a couple of lessons to prove it, but which kind of kind of tell you what we are, what we are going to look for when we look for the phase transition. Okay, in particular, the theorem is going to tell you who beta c is, but with some different definition of beta c. Weak to strong disorder phase transition. Okay, the idea is weak disorder is going to be behaving like simple random walk. Strong disorder is going to be being localized. Theorem. Okay, and yeah, if you want there were several stages for proving this, but just to give you the idea of when people have studied this and when they have proved that. So, okay, relatively recent work. So, okay, first thing, the sequence Wn beta omega n larger than 1. Okay. Okay, let's define omega 0, W0 is equal to 1. Okay, it's a natural definition if you want, but converges almost surely to a limit W infinity beta omega. Okay, the second thing is we have P W infinity beta omega belongs to 0, 1, and the expectation of W infinity beta omega well is equal to 1 if okay, so you have two options. Either this limit is 0 almost surely, or it's strictly positive almost surely. Okay, and yeah, if it's strictly positive almost surely, then the expectation of it is 1. Okay, and if it's 0 almost surely, the expectation is 0. But, okay, and last but not least, I forgot about this part. There exists beta c in 0 infinity such that okay, so the red part is the part proved in 2024. Okay, and this regime is called weak disorder. And the other regime is called strong disorder. Okay, so is it clear what the result says? Any? Okay, so perhaps it's clear what the result says. Maybe it's not very clear why this is relevant to us and why this guy deserves to be called beta c. Okay, so let's try to understand this. Okay. So let's start with the weak disorder phase. Okay, so why is this relevant to us? So if you have weak disorder, what you have is that, well, z and beta omega, it's when n goes to infinity, okay, it behaves like, well, up to some constant factor, okay, it's a random constant factor, but it's a constant factor nonetheless. Okay, if you look at asymptotics in n, Zn behaves asymptotically like its expectation. Okay, so now let's look at Zn. What it is. Zn. Well, it's the sum over x in omega n exponential minus h x beta. Okay, and this is n omega. Okay, so, well, it's a sum of Gibbs weights. Now, if you look at for x fixed, okay, x and omega x, well, it's typically of order well, beta n times the expectation of omega 1, 0. Okay, plus little o of n. Okay, just weak law of large number. Okay. On the other hand, the expectation of this exponential, well, this is exponential lambda beta n. Okay? And if you look at lambda beta, well, it's a log of the expectation of exponential beta omega 1, 0. Well, it's strictly larger than beta 1, 0. Okay, this is just Jensen. Okay, we are considering the case where omega has a non-trivial distribution. Okay, here you have a strictly convex function. Strictly convex function, non-trivial distribution. Jensen is a strict inequality. Okay, so therefore, like if you take one fixed term, okay, this thing is typically exponentially smaller than its expectation. Okay, so when you're saying that Zn is comparable to its expectation, it means that by taking the sum over all x's, basically, things average out, which is not a small feat because each contribution is much smaller than the expectation, I've already said. Okay, so if things average out, basically, it means that in spirit, basically, each x brings its expected contribution. Okay, some brings, I mean, most of them brings much less, some brings much more, but on average, they bring what they are expected to bring. Okay, and what this means is that basically, well, it's almost as if each x, like, you can basically replace the Gibbs weights by their expectation without changing much the measure. Okay, I mean, we are going to see proof that actually use this. So it's not some completely crazy idea, but the idea is that, yeah, because things average out, it's as if we can replace this by the expectation. If you replace this by the expectation, well, you have Gibbs weights that do not depend on x, so you have the simple random walk. Okay, so okay, you have because of what I've just said, you might expect simple random walk behavior. And on the opposite, if you don't have averaging, okay, you might expect something else. Okay, I think this is a rather weak point for this, but we are going to see stronger points later in the course. Okay. So, any questions that far about? Ah, yes, no, I had a better remark to make about the strong disorder case. Yeah. So if you are in the strong disorder case, basically, yeah, the sum does not behave like the sum of the means. It's smaller. And because of this kind of behavior, you might expect something like sum of heavy-tailed random variables, where you have no mean. Okay, and when you, for sum of heavy-tailed random variables, you know that they are dominated by the largest values. Okay, and okay, I've already told you that this sum is not going to be strictly dominated by largest values, but this is why you might expect some localization phenomenon to expect to come from there. Okay, I mean these sums. Okay, these variables. Okay, in a sense, when you're in the strong disorder, they are in a sense heavy. You have a sum of heavy-tailed stuff, but they are not. They are correlated, and the structure of correlation is a bit tricky here. Okay, but nonetheless, this is the point that I wanted to convey to convince you that this result is relevant. Okay, so none of these things are super complicated to prove, except for the red part here, which we are not going to prove. But it relies on some key observation, okay, that dates back to the 80s. And this observation is that this sequence here is a martingale. Okay, so how many of you know about martingale? So you don't know about it. Okay. So I'm going to give the definition. Basically, I'm going to end today's lecture with some statement about martingale, and then you will tell me if I need to prove it or not. Okay. So so I will recall the definition of a martingale. So and well to to say that something is a martingale, you need something which is called a filtration. So yeah, I'm going to consider Fn, which is a sigma algebra which is generated to the environment up to time coordinate big N. Okay, so you know all the environment up to time N in the whole space, nothing about the future. So this gives you an increasing sequence of sigma algebras, and this an increasing sequence of sigma algebra is what is called a filtration. Okay, and the definition here is given a probability space and blah blah blah. So given a filtration, and a sequence of integrable random variables, we say that Mn is a martingale with respect to F if for all n larger than m, the expectation of m knowing Fn is equal to m. Okay, so if you if you condition Mn to a filtration to a sigma algebra with lower index, what you get is m at the lower index. Okay, and yeah, okay, you can also assume that it's an adapted process in the sense that Mn is Fn measurable, but somehow this is implied by this, okay, in a sense. Because here you have, well, that the conditional expectation with respect to Fn is equal to Mn itself. Okay, and yeah, an observation is that you only need to check the property for consecutive ranks. Okay, so to check that Mn is a martingale, one only needs that the expectation of Mn plus 1 knowing Fn is equal to Mn. Okay. Okay, and perhaps here plus Mn is Fn measurable for all n. Okay, so why is this true? Well, simply because if you have this, then you can get this for n plus 2, n plus 3 by induction. So let me write this. Okay, you just use a power property for conditional expectation. Okay, and then okay, by induction you get this for every m larger than every ordered couple here. Okay, so yeah, perhaps the last thing we will do today is well to prove that. This is a martingale, so let me. And then what you have for free is that. So okay, basically this property doesn't sound like much, but it implies lots of stuff. In particular, what you have is that if a sequence is a martingale and is non-negative, then for free you know that it converges. Okay, so this is already, I think, point A of the theorem. Okay, so what's the proof here? Okay, we just have to show that this is equal to Wn. Okay. So now I'm just replacing Wn plus 1 by its expression. Okay, then okay, I can apply Fubini, or like Fubini for conditional expectation. Okay, so this is the expectation of, okay, or I mean, if you want, this is just a sum. Okay, so this is I mean, if you restrict the random walk to the first n plus 1 steps, this is just a sum. Then you have the expectation of exponential sum of n equals 1 to n plus 1, beta omega n xn minus lambda beta. Knowing fn. Okay, so now, okay, you're fixing the trajectory x. You're taking this conditional expectation. Well, this thing, it's the exponential of the sum, so it's a product of exponentials. Except the last one, all the terms, they are measurable with respect to fn. Okay, so when you have things that are measurable to respect to something, you have the right to take them out of the expectation. So this is what we are going to do. Okay, so okay. Exponential sum from n equal 1 to n beta omega n xn minus lambda beta exponential beta omega n plus 1 x n plus 1 minus lambda beta fn and that's it. Okay, and now we are basically done because, okay, now this variable here, it's okay. It's not an, I mean, it's not measurable with respect to that, but it's independent of that. Okay, just by the block argument for independence, basically. So because this is independent of that, the conditional expectation is just the expectation. And the expectation of that, by definition, it's equal to 1, because this is exactly what compensates for that. And now the expectation of this is exactly Wn. Okay, so this is here you can already see one thing, that at the core of our reasoning, we are really using the fact that things are independent in time. Okay, like being IID in space. Okay, perhaps it's the most natural setup to start with, at least, but it's not super crucial for the proofs. If you lose independence in time, basically, things get a lot more complicated. There are some stuff you can do, but yeah, I think this is the reason why people people were interested in studying this directed model. Here, it's very, very crucial that each omega here in the sum can be visited only once. Okay, like each space-time sites, okay, can be visited only once. If you had just an omega of xn, like even if x is a trajectory that feels some kind of drift, if it has the right to go back, then you cannot have basically this thing that at each time you visit something which is fresh and independent. Okay, so yeah, this is the reason why people have studied the directed model, yeah, the way you can the name of the model comes from the fact that you can imagine basically that yeah, you have a polymer that stretches in one direction, and these omegas basically they are, well, the solution in which the polymer lives, it's inhomogeneous, and some part of the solution they repel the polymer, some part of the solution it attracts it, but somehow the polymer is kind of forced by a field that stretches it, so it cannot go back. Okay, so we have proved the lemma, and now I will end with a question, basically. If Mn is a non-negative martingale, then Mn converges almost surely. Okay, so there exists M infinity such that limit when n goes to infinity of Mn is equal to M infinity almost surely. Okay, and this variable, the limit is integrable. Okay, so the question is, yeah, do you want me to provide a proof of this? Or should we move on? Okay, so I guess if everybody has seen martingale but one person, and if people that have already seen it are not interested in re-looking at this proof, yeah, my advice would be just, yeah, if you don't know this result, you can just accept it as a black box. The reason for this is not super crazy, okay? Basically, you can imagine that basically Mn is the amount of money you have after n rounds of a fair game, okay, where what you gain okay, is your expected gain basically is 0. Okay, your expected arithmetic gain is algebraic gain is 0, and basically, I don't know. My favorite proof of this result is you're going to say that, well, the probability that Mn is smaller than A and Mn is larger than B infinitely many times. Okay, so basically you want to say the probability that I oscillate between two values is 0. Okay, so if I oscillate between two values, this means that there has to be two rational values that satisfy this. Okay, the other option would be Mn go to infinity, but like, I mean, if you could gain infinite money with in a fair game, people would know about it. So yeah, why is it not possible that you go below A and above B infinitely many times? Well, it's basically that because of the Gambler's rule problems, when you're below A, the probability to go above B, it's bounded by A over B. Okay, so the probability that the probability to climb k times from A to B, it's smaller than A divided by B to the power k. Okay, and this, well, here, I mean, this is an upper bound for every k. So this thing has to be 0. Okay, and yeah, to prove this, basically, you need this stopping time theorem. So it's a bit of theory, but it's okay. It's in every standard textbook. I think the standard proof for this is not this one, but you can find this proof, I think, in Le Gal's book. Okay, and I will stop here for today.